This is going to be a pencast for Nuclear Review 1. This is going to be just pretty much the first half of the chapter. As you see on your screen, you already have all the writing, and I just want to tell you the first half or so, or 2/3, is all going to be about natural transmutation, and then there's just a little blurb down here about artificial. So when we talk about a nucleus, it can either be stable or unstable depending on the neutron to proton ratio. If something is stable, pretty much do nothing. If it's unstable, that's when it will decay. If it's unstable, it can decay either by alpha decay, giving off alpha particles, by beta decay, which would mean each nucleus would give off a beta particle, positron decay, which would give off a positron, or gamma decay, which actually is just giving off of high energy radiation, which does not have any mass or charge. Alpha particles have a positive charge. They have a mass of 4 atomic mass units, and they have a weak penetrating power. Beta particles have a negative charge. They have the same mass that's as an electron. It's 1/1836 of an AMU, and they have a stronger penetrating power than alpha. Positron has a positive charge, also has the mass of 1/1836 atomic mass units, and its penetrating power is going to be equal to that of a beta particle, which would be stronger than alpha. Gamma has no charge, gamma has no mass, and it has the strongest penetrating power. Neutrons have no charge. They have the mass of 1 atomic mass unit, and we don't generally talk about them in terms of their penetrating power. When we talk about half-life, half-life is defined as the time it takes for half of a radioisotope sample to decay into more stable products. We can find the length for different half-life periods on table N, and a sample problem would be if a 100-gram sample of iodine-131 is left for 32 days, how much iodine-131 is left unchanged, because remember the rest of it will be turned into something else. It will actually decay into a more stable product. So if we start off with our 100 grams of iodine-131, after the first 8 days, because I looked up and iodine-131 has a half-life period of 8 days. After the first 8 days, half of it will remain, so we will have 50 grams left. And again, that would be 1/2 remaining. After another 8 days, which would be the second half-life period, 25 grams would remain, which would be 1/4 of the original amount. After another 8 days, which would be the third half-life period, we would divide it in half again. 12.5 grams would be left. That would be 1/8 of our original isotope left. We still haven't gotten to 32 days because 8 plus 8 plus 8 is only 24. We need another 8 days to be half-life number 4 to get to our total of 32 days. After that fourth half-life period, we now divide in half again, which would give us 6.25 grams, or 1/16 of the original amount. So 6.25 grams of iodine-131 would be left unchanged after 32 days, which would be 1/16 of the original sample, and that would be 4 half-life periods going by. When we talk about artificial transmutation versus natural, for artificial transmutation, the nucleus is not just automatically unstable based on its neutron to proton ratio, so it has to be bombarded with high energy particles, and that will cause it to decay. Artificial transmutation always has at least 2 reactants, which, remember, reactants are the species before the arrow. Anything, if we're talking about natural or artificial radioactivity, and we're talking about the equations to find the missing species, in either case, the arrow acts as your equal sign. So on the left-hand side here, we have a total of 226 on the top. So we have to do 4 plus 222 to get to our mass number on the right-hand side. 88 is the total on the left here. So 2 plus 86. And then we look up on the periodic table, the atomic number 86 corresponds to Rn, which happens to be radon. Artificial, this one here would be a natural transmutation because there's only one species before the arrow. In order to do this for one that is artificial, this is artificial because I have two species before the arrow still acts as my equal sign, but now we'll just have to add together what's on the left to get the top number total. 27 plus 4 is 31, so over here I get a 30 because 30 plus 1 is 31. 13 plus 2 is 15, so 15 plus 0 is also 15. And 15 on the periodic table corresponds with phosphorus, so my missing species was phosphorus 30.